Hello, welcome to Mastery by. Today we are going to know about James Webb Space Telescope. Keep watching this video till the conclusion to learn a lot about the James Webb Space Telescope. And will James Webb Telescope see Big Bang? NASA created the James Webb Space Telescope, JWST, with cooperation from the European Space Agency, ESA, and the Canadian Space Agency, CSA. The telescope is named after NASA Administrator James E. Webb, who served from 1961 to 1968 and was a key figure in the Apollo program 9-10. It will take the place of NASA's flagship astrophysics mission. The Hubble Space Telescope 11-12 JWST was launched on Ariane flight VA256 on December 25, 2021. It will enable a wide range of astronomical and cosmological investigations, including observations up to redshift Z20-13 of some of the universe's oldest, most distant events and objects, such as the formation of the first galaxies and detailed atmospheric characterization of potentially habitable planets. And will James Webb Telescope see Big Bang? The new James Webb Space Telescope is so powerful it should be able to peer further back in time and create an image of the earliest galaxies in just a few hours. We will be able to see much closer to the Big Bang with the Webb telescope, maybe within 100 million. The optical telescope element, JWST's primary mirror, is made up of 18 hexagonal mirror segments composed of gold-plated beryllium that combine to form a 6.5 meter, 21 foot, 14 diameter mirror. This offers Webb's telescope a light-collecting area roughly 5.6 times larger than Hubble's 2.4 meters, 7.9 feet, mirror, 25.37 square meters versus 4.525 square meters. JWST will view in a lower frequency range from long-wavelength visible light, red, to mid-infrared, 0.6 to 28.3 m, than Hubble, which observes in the near-ultraviolet, visible, and near-infrared, 0.1 to 1.0 m spectra. This will allow it to observe high-redshift objects that Hubble can't see because they're too old, dim, or far away. To observe faint infrared signals without interference from other sources of warmth, the telescope will be deployed in space near the Sun, Earth L2 Lagrange point, a point in space about 1.5 million kilometers, 930,000 miles, from Earth, where its 5-layer kite-shaped sunshield can protect it from warming by the Sun, Earth, and Moon at the same time. JWST was developed by NASA's Goddard Space Flight Center, GSFC, in Maryland, and it is operated by the Space Telescope Science Institute. 19. Northrop Grumman was the primary contractor. The project started in 1996 with a $500 million budget and an initial deployment date of 2007-21. There were numerous delays and cost overruns, including a major redesign in 2005-22, a ripped sunshield during a practice deployment, an independent review board's recommendation, the COVID-19 pandemic, 23-24-25, issues with the Ariane 5 rocket, 26, and the telescope itself, and communications issues between the telescope and the launch vehicle, 27. The media and scientists remarked on the high-stakes aspect of the launch, which is expected to be the backbone of the next generation of study in its clarification needed domains, as well as the telescope's requisite complexity. After the construction phase was completed in late 2016, thorough testing commenced. JWST was launched from Kourou, French Guiana, at 12:20 Universal Time Coordinated on December 25, 2021, and was released from the upper stage 27 minutes later. The launch was described by NASA as flawless and perfect. As of January 2022, the telescope has been fully and successfully unfolded to its operational configuration, and is still traveling to its target destination. It will take several weeks to cool to its operational temperature, and then undergo final testing and calibration procedures for around 5 months, possibly including its first images, before beginning its planned research program. The James Webb Space Telescope has a mass of nearly half that of the Hubble Space Telescope, but it has a 6.5 meters, 21 feet, gold-coated beryllium primary mirror made up of 18 hexagonal mirrors, giving it a total size over 6 times that of Hubble's 2.4 meter primary mirror, 7.9 feet. The supplementary support struts obscure 0.9 square meters, 9.7 square feet, Therefore, its actual light collecting area is nearly 5.6 times greater than Hubble's 4.525 square meters, 48.71 square feet, collecting area. Beryllium is a non-magnetic, rigid, hard, lightweight metal that holds its shape even in extreme cold. It is commonly used in aerospace. Infrared reflectivity and endurance are provided by the gold coating. JWST is primarily built for near-infrared astronomy, although depending on the instrument, it can also view orange and red visible light, as well as the mid-infrared spectrum. It can detect objects up to 100 times fainter than Hubble, as well as things from considerably earlier in the universe's history, as far back as redshift Z20, about 180 million years after the Big Bang. For context, the first stars are thought to have formed between Z30 and Z20, 100 to 180 million years cosmic time. The first galaxies may have evolved around redshift Z15, approximately 270 million years cosmic time, and Hubble is unable to view beyond very early reionization at around Z11.1. Galaxy GN-Z11, 400 million years cosmic time. The design emphasizes the near to mid-infrared for three main reasons. High redshift, very old and distant, objects have their visible emissions shifted into the infrared, and therefore their light can only be observed today via infrared astronomy. Colder objects such as debris disks and planets emit most strongly in the infrared. These infrared bands are difficult to study from the ground or by existing space telescopes such as Hubble. The Earth's atmosphere, which is opaque in many infrared bands, must be viewed through ground-based telescopes. See figure of atmospheric absorption. Many of the target chemical compounds, including as water, carbon dioxide, and methane, remain in the Earth's atmosphere even when the atmosphere is transparent, greatly complicating research. Existing space telescopes, like as Hubble, are unable to investigate these bands because their mirrors are too hot. The Hubble mirror is kept at around 15 degrees C, 288 K, 59 degrees Fahrenheit, and the telescope itself radiates heavily in the infrared bands. JWST may also observe nearby objects with an apparent angular rate of motion of 0.030 arc-seconds per second or less, including objects in our own solar system. It may observe opportunistic and unplanned targets within 48 hours of a decision to do so, such as supernovae and gamma-ray bursts, as well as planets and satellites beyond Earth's orbit, comets, and asteroids beyond Earth's orbit, and nearly all known Kuiper belt objects. JWST will be in a halo orbit at the Sun-Earth L2, Lagrange point, about 1,500,000 kilometers, 930,000 miles, beyond Earth's orbit around the Sun. Hubble circles 550 kilometers, 340 miles, above Earth's surface, whereas the Moon is around 400,000 kilometers, 250,000 miles, away. Because of the distance, a crewed expedition to repair or improve the observatory, as was done for Hubble, is now impossible as of 2021. NASA officials mentioned the possibility of a servicing trip during the long JWST testing period, but no preparations were disclosed. Objects near this Sun-Earth L2 point can orbit the Sun in synchrony with the Earth, allowing the telescope to maintain a roughly constant distance with continuous orientation of its unique sunshield and equipment bus toward the Sun, Earth, and Moon to simultaneously block heat and light from all three, to avoid even the smallest temperature changes from Earth and Moon shadows that would affect the structure, and to maintain communications. This approach will maintain the spacecraft's temperature consistent and below 50 K, 370 degrees Fahrenheit, which is required for feeble infrared measurements. JWST must be kept below 50 K, 223.2 degrees Celsius, 369.7 degrees Fahrenheit, to make infrared observations. Otherwise, infrared radiation from the telescope would overwhelm its instruments. As a result, it employs a massive sunshield to block light and heat from the Sun, Earth, and Moon, and its location near the Sun-Earth L2 ensures that all three bodies are always on the same side of the spacecraft. Its halo orbit around the L2 point keeps the sunshield and solar arrays in a constant environment, avoiding the shadow of the Earth and Moon. The shielding keeps the structures on the dark side at a constant temperature, which is necessary for ensuring accurate alignment of the primary mirror segments in space. The 5-layer sunshield is made of Captain E, a commercially available polyamide film from DuPont, with membranes specially coated with aluminum on both sides and a layer of doped silicon on the sun-facing side of the two hottest layers to reflect the sun's heat back into space. One of the problems delaying the project was accidental tears of the sensitive film structure during testing in 2018. The sun shield was designed to fold 12 times to fit inside the payload fairing of the Ariane 5 rocket, which is 4.57 meters, 15.0 feet, in diameter and 16.19 meters, 53.1 feet, long. The shield's fully deployed dimensions were calculated to be 14.162 meters by 21.197 meters, 46.46 feet by 69.54 feet. Before being sent to Northrop Grumman in Redondo Beach, California, the sun shield was hand-assembled at Mantech, Nazolve, in Huntsville, Alabama. JWST does not have a limitless field of view at any given time due to the sun shield. The telescope can see 40% of the sky from one location and can see the entire sky in 6 months, which is the time it takes the Earth to complete half of its circle around the sun. JWST's primary mirror is a gold-coated beryllium reflector with a collecting area of 25.4 square meters and a diameter of 6.5 meters, 21 feet, 273 square feet. It would have been too big for existing launch vehicles if it had been designed as a single giant mirror. The mirror is made up of 18 hexagonal pieces that unfolded after the telescope was launched, Guido Horn di Arturo's multi-mirror telescope. Using very fine micromotors, image plane wavefront sensing by phase retrieval is employed to place the mirror segments in the correct location. They simply require periodic upgrades every few days after this first configuration to maintain optimal focus. This is in contrast to terrestrial telescopes, such as the Keck telescopes, which use active optics to continuously change their mirror segments to compensate for gravity and wind loads. Because there are limited environmental disturbances in orbit, the Webb telescope will use 126 tiny motors to adjust the optics on occasion. The optical architecture of the JWST is a 3-mirror anastigmat, which uses curved secondary and tertiary mirrors to give images free of optical aberrations over a wide field. The secondary mirror has a diameter of 0.74 meters, 2.4 feet. A fine steering mirror, which can vary its position many times per second to offer image stabilization, is also included. To save weight, the principal mirror parts are hollowed down towards the back in a honeycomb design. Under a contract from the NASA Goddard Space Flight Center in Greenbelt, Maryland, Ball Aerospace and Technologies is the primary optical subcontractor for the JWST project, which is overseen by prime contractor Northrop Grumman Aerospace Systems. Ball Aerospace and Technologies built and polished 18 primary mirror segments, secondary, tertiary, and fine steering mirrors, as well as flying spares, using beryllium segment blanks manufactured by Axis, Brush Wellman and Tinsley Laboratories.
That's it for today's video. Thanks for watching. If you like this video, then hit the like button and consider subscribing to our channel if you want to see more like it, as well as share it with your friends and family.